Dr. Saurav Chakrabarti, working as an associate professor in the computer science group at the Chennai Mathematical Institute, Tamil Nadu. Before joining Chennai Mathematical Institute, he was a postdoctorate at the Algorithms and Complexity Department of CWI, Amsterdam, Netherlands. He was a postdoctorate at the Computer Science Department of Technion, Israel. He was awarded PhD in Computer Science from University of Chicago. His area of research is theoretical computer science. His focus has been in the classical and quantum complexity of Boolean functions, including property testing, sensitivity, block sensitivity of Boolean functions, and quantum database search in electronic commerce, in graph algorithms, and in coding theory. He has published several research papers in both national and international journals.
Welcome to the UGC lecture series in computer science, and the topic is algorithms. So, today we will be looking at divide and conquer algorithms, and in particular we will be trying to solve the closest pair problem using the divide and conquer algorithm. So, to start with, what is the divide and conquer algorithm? So, divide and conquer algorithm is a technique where the idea is to break the problem into small sub problems, recursively solve the small sub problems, and carefully combine the answers of these sub problems. So, we have seen examples of that earlier. For example, we have seen things like binary search, heap sort, and so on. And in the last lecture, we saw usage of divide and conquer algorithm to finding the minimum and finding the minimum distance among points or integers in a set. So, as an example of divide and conquer algorithm, we saw this various set of algorithms. In today's talk, we will be talking more about this finding the minimum distance, but on a plane. To start with, we have to recap our problem for finding the minimum distance in a set. So, what was it? So, we have been given a set of numbers n, and we want to output the minimum value of I minus j, where I and j are in the set S. As we had noted last time, this can be thought of as the x axis, and all the I j's that have been given to us S are points on this line. So, these are I j's can be thought of as just the distance from the y axis or 0 coordinate. Once we have given that, so the problem is basically to finding out two points which are closest to each other. So, how did we try to solve it? As the first attempt, it is kind of clear that the algorithm that we have to use has to be a bit tricky. For example, if the set S is this given set, it is a random set of numbers, and if I want to output the closest point, it is not obvious at all. What is the 2 x and I and j such that I and j, I minus j is minimized. So, the first attempt was just to try out all possible pairs I and j and store the value I minus j in a set T, and then find the minimum of this set T. Now, this clearly is the right answer, because we are looking over all possible pairs. The problem is the running time of this algorithm turns out to be order n square, because the total number of pairs that we have I j in a set S is around order n square, and to output the minimum of the set T, which is now n square numbers, we have to use order n square steps. So, the total runtime becomes order n square. Now, question was, can one do better? And the idea was to use the divide and conquer approach. The idea is just to sort this set S in an ascending order. Once we sort this set S in an ascending order, we split this set S into two parts, the smaller half and the bigger half. We recursively solve this problem in the smaller half and the bigger half, and we combine it carefully. So, let us recall the example. So, here was the set S, and first thing was to sort this set S and split it into two equal sized sets S1 and S2. Note that they are sorted and then split. So, all the elements in S1 is less than all the elements in S2, or in other words S1 contains the smallest n over 2 elements of S and S2 contains the largest n over 2 elements of S. Now, what was the approach? The idea was that if I have an ij pair that achieves this minimum distance, then what properties can this ij have? The first of all, it either can be that both ij are in the set S1, or it can be that both ij's are in the set S2, or it can be that while one of them is in S1, the other one is in S2. Now, once we have split it into these small problems, so in this case the problems are solving it in S1 and solving it in S2. So, we recursively solve this problem on S1 and S2, and thus we obtain that the minimum distance of pair of points in S1 say is 3 and minimum distance on S2 is also 3, and then we combine them by saying that if ij are pairs such that I is in S1 and j is in S2, then the minimum is achieved only when I is in the maximum of S1 and j is the minimum of S2, and so in that case we find that I minus j is 2. So, we see that in this first option, when both I and j are in S1 we have 3, in both I and j in S2 we have 3, and when I is in S1 and j is in S2 we have 2, and thus the minimum distance can be obtained as 2. This was the pseudo code of this algorithm, and we saw in the last lecture that this algorithm achieves a runtime of order n log square n. Actually, we told that we can get an order n log n algorithm, which we will see today later on, and we also saw the naive algorithm that takes order n square. So, now let us try to generalize this problem, and here we get one of the most interesting problems and most used problems in the field of computational geometry or many other areas like machine learning and so on. So, now we have been given say n points in R2. By R2 I mean the plane, the xy plane that we have. We have been given n points. So, the points are p1 to pn. Now, once we have been given the plane, so what does it mean by these points? For each point we have been given the x coordinate and the y coordinate. So, x1 y1 is the first point, x2 y2 is the second point, and so on till x n y n. And what do we have to output? We want to basically find the 2 points that are closest to each other. Note that there are lots of points there. So, we want to find the 2 points that are closest. So, we want to output this closest pair p and q that belongs to this set S. And what do I mean by closest? The closest is the obvious one, that if the distance between p and q is the Euclidean distance, or the distance that we usually think of, which is the square root of the difference of the x coordinate whole square plus difference of the y coordinate whole square. This is something that we have done in our coordinate geometry class of how do you find the distance between 2 points. So, this problem is not only interesting on its own right, but it is an unbelievably important problem that is solved all the time. It is used in coding theory, it is used in cryptography, it is used in machine learning, because many times when we get some string or an input, we plot it in high dimensional space and we try to compute the smallest distance between these 2 points. So, this is the setting, and how can we go about it? So, let us see. So, basically we can view our input as something like this. So, we have been given the set S and we have to find the closest point pair p q such that p q are close. So, here I have chosen some randomly selected set of points and we want to find the closest point. Clearly, it is not obvious at all. So, you need to have some very interesting algorithms. So, let us see what can be the first attempt that one can think of. Just in the case of the line setting, where we were given only numbers. So, in other case we are just only given the x coordinates and we are asking the distance between the two numbers, one can just consider all possible PQ pairs. So, you can pick one pair PQ and compute the distance between those two P and Q. Now, that is a number. You store that number in your table or in a put them in a set T. Now, after you have compared all possible pairs P and Q, then you output the minimum value of all the numbers in this set T. Clearly, this will give you the right answer, because we have gone through all possible pairs P and Q and noted down their distance, and we have output the minimum value. So, the algorithm is clearly the simple algorithm, and it works, and it seems to be the right one. Now, what is the running time of this algorithm? Note that for the running time, we have to go over all the possible pairs of PQ in S. Now, if S has n points, then how many pairs are there? The number of pairs there are order n square. So, we have to go over order n square pairs, and after we have gone over order n square pairs, then we have to output the minimum of the values of set T. So, T has order n square values. So, finding the minimum will take order n square, and thus the total runtime is order n square. Now, again, just like in the case of the finding the minimum distance in a line, we have a naive algorithm or a simple algorithm that takes order n square steps, and question is that can we obtain a better bound? Can we obtain something like n log square n or n log n? This is where again we go back to divide and conquer approach, and this time the things will become much more interesting. So, let us go for a break now. After the break, we will see the divide and conquer approach for solving this algorithm. Welcome back after the break. So, before the break, we saw a naive algorithm for computing the shortest distance, the smallest distance between 2 points in a plane. Now, we saw that the running time of this algorithm was order n square. Now, let us try to use the divide and conquer approach to get a better algorithm. The idea is again simple. You use divide and conquer and a similar technique that we use for the one dimensional setting. So, here is the input and here is the pictorial example. We will see by an example how to do it. The idea is again same, break this problem into two sub problems, solve them in these two sub problems independently and recursively, and then try to combine them carefully. So, once we have this set of points, the first thing that we do is that we sort these points based on their x axis coordinate. Once we have sorted their x axis coordinate, so what do I mean by that? Note that if you look at this x axis coordinate, we find that okay, this x axis contains 2 points, this x axis contains 2 points, this x axis contains 3 points, and so on, and then we find out where does this cutoff or middle point is. So, thus we have 2 plus 2 plus 3 plus 2. So, we have something like around 18 points, and so we have to find out the halfway mark, which basically contains 9 points. So, this is kind of called the median line. So, once we have sorted, we have basically projected all these points to the x axis and we have sorted them based on the x axis, and after we have done that, we can find the median line. So, median line can be any line here such that exactly half of them are on the left and half of them are on the right. So, in this setting, this thing that is drawn here is the median line. Now, once we have the median line, we basically have split this problem into two sub problems, right, just in this case of the one dimensional setting. So, we have the left side, which is this side, and we have the right side, which is this side, and we can recursively solve for both the left side and the right side and then combine it. But the same problem happens. The closest pair P Q in S will be either of these three conditions. So, either P and Q are both on the left side, or P and Q are both on the right side, or P is on the left side and Q is on the right side, or vice versa. Note that again in the first two cases recursively doing it will output the right answer. So, in other words, we recursively solve for the closest pair of points in the left side and right side. So, in this example, say I have found D1 here, which is the closest pair, and D2 which is the closest pair here. This example is just an example. So, this thing is not up to scale. So, once we have this D1 and D2, we therefore know one pair that is at distance D1 and one pair that is at distance D2. And if at all there exists a point, say something like this point and this point or something like that, this pair is only interesting if their distance is less than D1 and D2. If the distance between them is greater than D1 and D2, then it is completely useless for us. So, that helps us in somewhat screening this possible set of pairs. In the case of one dimensional setting, this was very easy, that if P is in one side and Q is in other side, the closest thing can happen only which is the maximum of the S1 and the minimum of S2. In this case, that is not the case. The closest pair can very well be either this one, or it can be this one, or anything for that matter. We have no idea. But again, we are only interested in those P and Q pairs whose distances between them is less than D1 and D2. So, what we do is that we take the D which is the minimum of D1 and D2, because that is what we have to beat in some sense, and we draw two vertical lines which is the distance D from the median line. What is the idea? The idea is that if a point here, say this one, has to be interesting, then that better be at distance less than D from some point in Q, only then we will have to consider that point. And that cannot happen, say if this point is at distance D from this median, then all the points on the left hand side will also be at distance greater than D. So, only points that kind of are interesting now to us are the points which are in this band. Points which are outside this band are not useful at all, because they will not contribute to the shortest distance by taking P from the left hand side and Q from the right hand side. But the catch is that still it is very much possible that inside this band there are lots of points. But if there are lots of points, we again cannot do an exhaustive search, because there are so many points, we will be basically be again using order n square steps, which is not good. So, what can we do? The idea is that, do we need to really look at pairs like this and this? Answer is no, because these two maybe are so far apart, or in other words, their y axis coordinate will be differing at a distance d. If their y axis coordinate differs at a distance d, then they must be more than d far apart. So, we can screen out such kind of pairs also. So, how do you do it? We make this following claim, that for any point on the left hand side, there are at most 6 points on the right hand side which are at distance less than d. So, why is this thing coming up? So, let us consider this point. Now, for this point I have drawn this box. What is this box? This distance is d. So, basically idea is that anything that is higher than this line or lower than this line, so this distance also d, is useless. Now, all we want to compare is, for this point we only want to compare those points that are inside this box. Again, inside this box, how many points can there be? Technically there can be lot, but can there be a lot? The idea is that already we know the distance between any 2 points here on the right hand side is greater than or equal to d. So, here is this point. So, I cannot expect that if this is a point, the another point is right here or another point is right here, because I am guaranteed that d2 was the smallest distance. So, this distance must be greater than d2, greater than or equal to d2, which means it must be greater than or equal to d. So, this brings us that how many points can we put in this box of width. So, this is width 2d and this is width also 2d. In this box or rectangle of size 2d by 2d or the 2d by d, how many points can I put such that any pair of them is at distance d apart. I leave it as an exercise for you guys. It is a geometry problem and one can see that one can at most put 6 points. The idea is kind of very simple, that if I have a box like this and if I put a point here, then if I draw a circle around it at distance d, I cannot put anything between this point and the circle, because then this distance will be d. So, I again have to put this and then I put another ball and so on, and then you can prove that at most d 6 points can be put inside this rectangle. So, thus we have that for every point on the left, at most 6 points on the right are at distance less than d, which means that these are the only interesting pairs for us. So, the next step is identify all the pairs p q such that p is on the left hand side of the box of the band and q is on the right hand side and the y axis is less than d. I mean, this is a bit relaxation of the fact that the distance is less than d. So, we say that even at least the y axis is less than d. This can be done by sorting the set of points according to the y coordinate, because if we sort the set of points according to the y coordinate, then we can just make one pass through the set and we can find out all the p q pairs which satisfy this condition. What we know is that total number of p q pairs must be less than 6n, because for every point in p there are at the most 6 points which are at distance like this. So, what we do, once we have just 6n pairs, we go over all of these pairs exhaustively. So, thus we find d 3 which is the minimum distance among all such pairs, and then we output d minimum of d 1, d 2 and d 3. So, the idea is that d 1 is the minimum distance in the left hand side, d 2 is the minimum distance in the right hand side and d 3 are the minimum distance in the middle, or which means that one of them is in the left and one of them is in the right. The idea was to combine these two things, and that is where the ingenuity of this algorithm comes. So, let us see the pseudocode of this algorithm first. So, first we sorted these points according to the y coordinate and find the minimum median line. Then we recursively solve the for the left hand side of the set and the right hand of the side of the median. Let d 1 and d 2 be the smallest distances in the left side and the right side respectively. Take the mean of d 1 and d 2. Identify all the pairs p q such that p q is in the left side of the line and q is on the right side of the line, and the distance from the median is less than d in both the settings, and the y axis differs in less than d. So, this is what we say that is less than 6n, and after that find the minimum distance among all such pairs, and then you output d 1 minimum of d 1, d 2 and d 3. So, the correctness of this algorithm is something that I have explained. I am not going to go into the details of it right now, but let us go over the running time of the algorithm. Again, like in any other divide and conquer algorithm, let T n be the number of steps required to find the closest pair among n points. Then what do we have? In the first case, we have to sort, so it takes order n log n steps. Then we recursively solve for the two halves. So, we take T n over 2 in the left half and T n over 2 in the second half. So, we have twice T n over 2. Then we do this, find the median, and then we identify these points. For identify all these pairs, again we have to sort all the points according to the y axis, and in the worst case this can be order n log n. And then we have to find minimum among all such pairs. Since the total number of pairs is just 6n, so the minimum will take order n number of steps, and then to output it, it is just an order 1 step. So, the total runtime is, we have some n log n's and some n's. So, we combine all of them to get t of n is order n log n plus twice t n over 2. This is something exactly we have seen for the one dimensional setting, and we can get that t of n is order n log n square. So, we have the naive algorithm that gave us order n square steps. Then we had the divide and conquer approach, we gave order n log n square. So, actually square here, and question is that can one get an order n log n algorithm? The idea is simple, that we have to do this sorting on the x axis and y axis, and once we have sorted it in based on the x axis and y axis, in the recursive calls we do not need to sort it again, because it is already sorted. So, in other words, if the set is sorted, we can just go ahead and then we will be done. So, in the set of, in that case, the pre-sorting, the sorting it beforehand will take order n log n steps. After we have sorted it on the sorted list, it will take t of n equals to order n, because remember that n log n only appeared when we were doing the sorting and not for no other purpose. So, we get t of n equals to order n plus twice t n over 2, and thus we get t of n is equal to order n log n. So, you have a pre-sorting step that takes order n log n, and other on a sorted list it takes order n log n. So, the total runtime becomes order n log n. So, the naive algorithms takes order n square, and a clever divide and conquer approach takes order n log n. So, to summarize today we saw or recap the algorithm for finding the minimum distance or minimum difference, which is the minimum distance on a line, and then we generalized it to obtain an algorithm, a divide and conquer algorithm for finding the closest pair on a plane. With this we come to the end of this lecture. In the next lecture we will see one more interesting application of divide and conquer approach. Thank you.